This is Nicholas Moya, and for my project, we're going to be talking about using optimal control to control satellite trajectories using bounded control signals. So in this presentation, we're going to talk a little bit about the motivation behind this idea. We're going to formulate the problem into a more optimal control perspective. We're going to talk about the solution to this, which is to use linear tracking. And then we're going to look at my results from my MATLAB simulations, and we're going to talk about what those results mean, the problems and solutions that were encountered. So an interesting fact about the moon is that the same side of the moon always faces the Earth. Now this is good and bad, but one of the reasons that this is bad is that if there's ever an expedition on the far side of the moon, it will have trouble maintaining a communication link to Earth. One of the ways to solve this is to use a satellite relay system. A relay satellite is just a satellite that is positioned near the far side of the moon so that it can keep a communication link between the moon and the Earth. However, we don't want this satellite to be in a regular orbit around the moon. We want it to be in a special orbit called a halo orbit. That way, it can maintain line of sight with the Earth and the moon at the same time. A halo orbit, again, is just an orbit that is around a point in space rather than around a celestial body like we're normally used to. Here is a quick little animation of a satellite in a halo orbit. As you can see right here, we're getting about a top-down kind of perspective on it. The gray sphere here is the moon, the blue sphere here is the Earth. And just to give you some historical background, the first mission to use a halo orbit was the ISEE-3, which was launched in 1978, and it traveled to the Sun-Earth L1 point and remained there for several years. Now, the L1 point is referring to Lagrange points. Lagrange points are points in space where the combined gravitational forces of two large bodies equal the centrifugal force felt by a much smaller third body. What that means is, if there's an asteroid or a satellite in one of these 5 Lagrange points, it will actually stay in that point relative to the orbit. Just to give you a visual diagram, here I've included the Lagrange points with the gravity wells of the orbiting bodies. You can see if a satellite or asteroid is too close, it will just orbit or fall in to one of the gravity wells. If it's too far, it will fall away. However, if it's positioned within one of these 5 points, it's a relatively stable position, and it will stay there throughout the period of orbiting the bodies. And just to give us a real-life example, this is the orbit of Jupiter, and as you can see, it has clumps of asteroids, those are the green dots, that are found in its L4 and L5 points. The asteroids will naturally go there because it's a stable position, and then they'll just orbit around the same orbital path as Jupiter in those positions for the duration of the orbit. So now that we've talked a little bit about our problem, namely having a satellite in a halo orbit, we're going to start talking about the states of our satellites or our satellite system. But before we do that, we want to first simplify it. So what we're going to do is we're going to linearize our satellite system around one of the Lagrange points. This makes our nonlinear satellite system a linear one. Next, we're going to approximate our halo orbit to be a circular orbit. That way, the satellite system will go from being a time-varying system to a time-invariant system. Using these two methods allows us to simplify our satellite system into a simple LTI system. So here are the raw dynamics of the satellite system. They're presented here on the left with nomenclature on the right. The main takeaway, though, is that we care most about the position, velocity, and acceleration of the satellite in the X, Y, and Z directions. Making the approximations and substitutions on the right into our raw dynamics, we can simplify it into a more easily digestible state space representation, where the 6 states that we care about are the position and velocity of the satellite in the X, Y, and Z directions. Here we've also included our control signals, U1, U2, and U3. For the satellite, we're assuming that a thruster is positioned on all 6 sides of the satellite, so it will be able to control the satellite's motion in the positive and negative x-axis positive and negative y-axis, and positive and negative z-axis. Also, our force here, our control signal here is force. It's the force of the thrusters. So we attach those to the acceleration states, and then we just multiply by 1 over m, because force equals mass times acceleration, and that way all the units stay the same. So the main problem that we're dealing with is we have a satellite in a halo orbit, and we want to keep it in that halo orbit. That means that we want the position and velocity states of that satellite to match a halo orbit trajectory. So the solution to this problem, of course, is just to use linear tracking. Linear tracking allows you to keep states in a system and make them track desired reference trajectories, which is exactly what we want to do. So to begin this, we want to look at the performance measure. Here's the general form of the performance measure given right here. We'll talk more about this, but the main takeaway here is that we're going to set 3 things. One, the H matrix is going to be 0. That's because we don't have a final state or final reference trajectory. We want the orbit to continue infinitely. So we're going to set those to 0 because we don't have a defined endpoint. Next, we're going to set the Q matrix to be a 6x6 identity matrix with a large gain. That's because we want to minimize the difference between the states and the reference trajectories. And conversely, we're going to set the gains on the R matrix to be very small. We do that because we don't want our control signal to be minimized. We want it to be as free and dynamic as possible. All right, so the next step is to define our control law. So this is the general form for the control law for linear tracking problem. And as you can see here, the control law mainly depends on K and S. K and S are Riccati equations. The equations are given right here with their boundary conditions here given for final time. So once we solve those, we can start to see the results of implementing this system into our MATLAB simulation. So here's the solution for plotting the Riccati states. As you can see, they're mostly constant until they have to drop all the way down to 0, as is their bounded condition. Here's the S vector. As you can see, it's quite large, which is needed to keep the states tracking the reference trajectories. And we're going to get to the states. Now the states here are plotted in blue and the reference trajectory is plotted in orange. As you can see, they track each other very, very well. Now just talking what exactly are our reference trajectories, they're given right here. So for our 6 states, position and velocity in X, Y, and Z direction, we want the position to follow a sine wave, which we have here. We want the velocity to track the derivative of our position, of course, which is just given right here. Same thing for y. We want our y position to follow this cosine wave. So we want the velocity in the y-axis to follow this sine wave. And then for our last 2 states, the position and velocity in the z direction, we want those to be 0 because here the orbit is on the xy plane and then the width of that orbit is on the z plane, and we don't want it to wobble a lot, so we want z to be 0. And so as you can see here, the results are pretty good. Our states track the reference trajectories very well. As you see, like in the first 10 hours, it matches perfectly, and then they deviate very slightly, but it's still pretty good results. The last thing to look at, and the most important thing to look at, is our control law. Now, for the satellites, they can only produce a certain amount of thrust from the thrusters. They can only produce a certain amount of force. And that force is about plus or minus 1 Newton. So we bound our control law before we implement it into our state space design, and that's a plot of it right here. As you can see, jumps down to -1, then back up to 1, then back to -1, and then it continues on right there. So we were able to get our states to track our desired reference trajectories with a bounded control law. All right, so in the conclusion, we're just going to talk about some problems and solutions that I encountered during this project. The main 3 problems that I encountered were solving the Riccati equations, creating the control law, and then choosing the Q and R matrix gains. So, for solving the Riccati equations, Now, the Riccati equations are huge. The K state alone is a 6 by 6 set of ODE equations. The S state is a 6 by 1 matrix. So obviously, we need to use numerical integration because there's no way we could find a closed form. However, if you use a numerical integration function like I did, I used MATLAB's ODE45, you'll notice that MATLAB's function, ODE45, assumes an initial condition, but we're not given initial conditions. We're only given boundary conditions. So how do we do this? Well, very simply, all we do is we flip the bounds of integration. So instead of integrating from initial time t0 to final time tf, we integrate from final time tf to initial time t0. Now, if you plot this, it'll look great. However, you need to realize that because you integrated it backwards, your data points are actually in the reverse order. So before you do anything, before you use these for anything, you need to flip or reverse the order of the data points for your solved Riccati equations. So you need to set the last element first, second to last element second, and etc. Then they'll be in the correct order. The next thing that I had trouble with was generating the control law. Now you see the general form of the control law right here, and you might think, well, I know my x and my s, I just plug it in, and then I'll be able to find my control law. However, in reality, the elements for your k and s matrices, they're not singular. They're not just a number. They're a huge set of data points. So if you plug this into MATLAB, the dimensions aren't going to be right, and it's not going to multiply and give you a valuable result. So the solution to this is to store your K and S data points into a library in the correct order so that they can be recalled later. And then when you recall them when you're doing the integration for the state space. So inside the integration itself, you're going to skim off a level of your K and S data points to form your K and S matrices. And then you'll be able to use that to form the control signal and add it to X to be numerically integrated. Explaining that more as an algorithm, I have here on the left, first we set our parameters, we're going to solve the Riccati equations, then we're going to reverse the order, and then we're going to store them in a library for recall. Then, during each step of integration, we need to skim off the ith data point of the Riccati solutions library, use that to form our f and v vectors, and then use that to generate u. Lastly, we're going to bound u and then add it to our state space so that it can be integrated numerically. Now, another key point here is that you have to use your own ODE solver function. That's because most ODE solvers are clearly defined and you can't crack them open and go inside to add your K and S data points at each step of integration. So you need to include your own user-defined ODE solver function and then go inside and then add your K and S data points to create U and then integrate for X. Lastly, the last problem I encountered was setting my Q and R matrix gains. Now, when I was working on this problem, I got my code to work. However, it wasn't giving me the results I wanted. So what I did was I looked at the Q and R matrix gains. Now, Q sets the penalty for the difference between your states and the reference trajectories. And we're trying to minimize this J. We're trying to minimize the stuff in this integral. So if we set a large Q gain, we're going to increase the penalty for the difference between the states. And that helps our system track the states to the reference trajectories more closely. On the other side, we're going to set a small gain for our R matrix. That way, the performance measure doesn't minimize or diminish our control signal because we want it to be as large as it needs to be. Now, in the beginning, I thought that this was bad because, again, I have bounded control signals. However, it turns out that even setting R to be very small so that my U is not controlled or diminished, I can still have bounded control signals and it will still control my states to track my reference trajectories. So that's my project. Normally I'd ask for questions at this point. However, since this is going to be on YouTube, just feel free to email me any questions you have, and thanks for listening.